Hello guys, welcome back to video. And this video is about DNF blocks. Important questions going to be asked in second PUC midterm. These are really important guys. So let's get started. Transition elements. Why do transition elements show variable oxidation state? Because they have partially filled n minus d. Because they have partially filled n minus 1d and ns orbitals, and the energies of these orbitals is very close. Okay, is very close and very similar, so both can participate in bonding. As a result, a different number of electrons can be lost. For example, iron has +2 and +3. That's so the question is that why are transition elements show variable oxidation state, partially filled n minus 1d and ns orbitals, and the energies of these orbitals is very close, so both can participate in bonding. As a result, different number of electrons. Highest oxidation, what is the highest oxidation state in 3D series? Is manganese. Okay, maximum in KMnO4 is +7. Transition elements show magnetic properties due to presence of unpaired electrons in their n-1d orbitals. The spin of these unpaired electrons produces a magnetic moment. The greater number of unpaired electrons, the stronger the magnetic property. Okay, transition elements show magnetic properties due to presence of unpaired electron in their n-1d orbitals and not ns. Okay, the spin of these unpaired electron. Next, in transition elements, the orbital contribution to the magnetic moment is often negligible due to quenching by the ligand field. Hence, the magnetic moment mainly arises from the spins of unpaired electron. Therefore, spin-only formula is used to calculate. Question is that why is only spin-only formula used and not this orbital? Why there is no orbital contribution? Because in transition elements, orbital contribution to magnetic moment is negligible due to quenching by the ligand field. Hence, magnetic moment mainly arises from spins. Next is spin only formula. This is important. This is mu is equals to under root n into n plus 2 Bohr magneton, where n is number of unpaired electrons. Transition elements act as catalyst. The reasons are they can change oxidation state easily, helping in oxidation reduction reactions. They can provide large surface area. They can form intermediate complexes with reactants, lowering the activation energy. For example, iron in Haber's process and vanadium pentoxide in contact process. Okay, the reasons are change in oxidation state easily, large surface area, intermediate complexes with the reactants, and lowering the activation energy. Hence, the transition elements exhibit coloring properties. Why? Because of dd electronic transitions within the partially filled d orbitals. When light falls on these compounds, so certain wavelengths are absorbed for electron excitation, and remaining light gives the observed color. Cu+2 salts are blue due to dd transitions. Okay. What is lanthanide contraction? Lanthanide contraction is a gradual decrease in atomic and ionic radii of the lanthanoids, cerium to lutetium, with increasing atomic number. And what is the cause? The cause is poor shielding of 4f electron. As the number of 4f electron increases, the effective nuclear charge increases, pulling electron closer to the nucleus. And what are the consequences? The causes, the consequences. The elements of the second and third transition series have almost similar sizes, and separation of lanthanoids becomes difficult due to their similar sizes and properties. Now, what is an actinic contraction is more than lanthanoid contraction, because 5f electrons are poorly shielded compared to 4f electron in lanthanoids. Hence, there is a stronger attraction between the nucleus and outer electrons, leading to greater contraction. Common oxidation state shown by lanthanoids and actinoids is +3. Actinoids show variable oxidation state because the 5f, 60 and 7s orbitals are close in energy, just like in lanthanoids. Hence, electrons from all these orbitals can participate in bonding, giving rise to multiple oxidation state. Manufacture of K2Cr2O7 from chromite ore. There are step 1, step 2, step 3. There are 3 steps. Okay. First is conversion of chromite to sodium chromite, conversion of sodium chromite to sodium dichromate, and conversion of K2Cr2O7. Okay. Conversion of chromite to, so we are making chromite, so we are making potassium chromite from chromite ore. Okay. Conversion of chromite to sodium chromite first. Chromite ore, that is FeCr2O4, FeCr2O4 is fused with sodium carbonate. And quick lime in the presence of oxygen. You'll get this. And we are taking this sodium chromate solution is acidified with dilute sulfuric acid. Okay, acidified with dilute sulfuric acid to give sodium dichromate. Now conversion of K2Cr2O7. When Na2Cr2O7 is treated with KCl, less soluble K2Cr2O7 crystallizes out. Next is preparation of KMnO4 from pyrolusite MnO, which is MnO2. There are 2 steps, 1 and 2. Formation of K2MnO4, conversion of K2MnO4 to KMnO4, because that's what we are preparing, right? So pyrolusite is fused with KOH in the presence of air, or KNO3, to get K2MnO4. Now potassium manganate is oxidized to potassium permanganate by electrolytic oxidation and disproportionation in acidic medium. Okay. Properties of lanthanoids and actinoids is basically the differences: electronic configuration, radioactivity, oxidation states, and nature. Involved in 4f orbitals, 5f orbital. Radioactivity mostly non-radioactive, are radioactive, mostly positive, +3, plus here +3, +4, +5, +6. Here it is less metallic, more metallic, and reactive, because metals are reactive, obviously. Next is interstitial compounds, the compounds which are formed when small atoms like hydrogen, boron, carbon, nitrogen occupy the interstitial sites or voids in the metal lattice. The properties are: they have hard and have high melting point, they retain metallic conductivity, and are often chemically inert. What are characteristics of transition states? They have partially filled d orbitals, they form colored ions, complex compounds, exhibit variable oxidation state. Now Cu2 plus is colored and Cu plus is colorless. And why? The answer is Cu2 plus. The configuration is this, which has unpaired electron that undergo dd transition giving color, and here has a no unpaired electron, so no dd transition, it is colorless. Simple. Zinc does not exhibit variable oxidation state because its electronic configuration is this. The d subshell is completely filled, so it shows only +2 oxidation state. Okay. Now it is showing oxidation state, but it is not showing variable oxidation state more than 2. Scandium +3, उसका इलेक्ट्रॉनिक कॉन्फ़िगरेशन लिख लेना, फिर कितने निकाले हुए हैं उतने निकाल दो, ठीक है. And how many unpaired electrons are there? 0. And 0 into 0 you will get like this. Okay. And next, titanium. So its real configuration is this. When you remove 3 from this, you will get like this, and there is 1 unpaired electron. Substitute, you will get this. Okay. Do this for Mn2 plus. Next is catalytic properties of transition metals. Variable oxidation state, formation of complex compounds, large surface area. They can form intermediates and easily change oxidation state. Formation of complexes, they absorb reactants and weaken bonds. Large surface area, they provide active sites for reaction. Fe and V2O5 in Haber's process, contact process. NH3 manufacture, H2SO4 manufacture. Next, Transition metals can form large number of complexes because small size and high nuclear charge break in d orbital. They show variable oxidation state. And that's it for the video, guys. Thank you for watching, and like if you like the video, subscribe and share to your friends if you want. If you don't want, don't share. So that's it. Hope you like the video. Thank you.